Video 5, last one. I'm going to talk about two things in this video. First one is ionic radii. And what we're talking about here is how did the size of, let's say, for example, a cation correspond with the radii of its neutral parent atom. So let's think about this. When you go from a neutral atom to a positive ion, you're taking an electron out from one of the outermost shells. Those outermost electrons sort of define the boundary of that particular atom or ion. Now, and also, since you have fewer electrons, the overall electron-electron repulsion is reduced. So, do both of these make the cations larger or smaller than their neutral parents? And if you guessed smaller, then you guessed correctly, or reasoned correctly. Now what about anions? So you are adding an electron to an outermost shell, which is going to increase the spatial extent of that particular atom. And since you are adding an additional electrons, the overall electron-electron repulsion is increased, so the whole electron cloud puffs up a little bit more. So anions are bigger or smaller than their parents. And if you guessed bigger, then you guessed correctly, or reasoned correctly. And just to give you an idea of how this changes, so these are representations of the radii of various elements and the ion they are most likely to find. So lithium is usually +1, sodium is usually +1, and in this case the radii goes down by roughly half, by roughly a third for sodium, and so on and so forth. The difference is more dramatic the more electrons you take out. So in this case, lithium drops down by a factor of 2, beryllium drops down by a factor of 3, boron drops down by almost a factor of 4. Here on the other side here, we're looking at atoms that typically form negative ions. Like in the case of going from oxygen to oxide, that's almost a doubling in size. And similar to fluorine going to fluoride. So the greater the magnitude of the charge, the greater the difference between the ion and its neutral parent. So that is how ionic radii compare to their neutral parents. So another thing that you could do is talk about the size of a bunch of species that have the same number of electrons. That's what isoelectronic means. For example, all of these species, sulfide, chloride, potassium, and calcium, have the same number of electrons, in this case 18. So what I want you to do is figure out which one of these is, rank these in order of size. Going from, all right, now I'll tell you that they are ranked. The question is, are they ranked in order of largest to smallest, or smallest to largest? And why? So these are the actual radii for these ions. So they go from 1.84 angstroms for sulfide down to 0.99 angstroms for calcium. Why is that? Well, think about what's the same in these and what is changing. So all these have the same electron configuration, that of argon, the same number of electrons. But what is continually changing is the number of protons in the nucleus. So same number of electrons, increasing number of protons, that will have the effect of drawing them in closer, making those radii go down in that direction. So the radius will go down as the nuclear charge goes up. Last thing, sort of, is successive ionization energies. So this graph here shows you the first, second, third, fourth blah ionization energies for the third row, sodium, magnesium, aluminum, silicon, phosphorus, all the way up to argon. You will note that some of these are sufficiently large that they are difficult to actually measure, so that's what this unfilled in blue area is here. Now, a couple of things to notice. First of all, they are always positive. And that's because you're always taking an electron, a negatively charged particle, away from an increasingly positively charged particle. And for any element, they always increase. First one is always the smallest, followed by the second, followed by the third. So successive ionization energies always require more energy. And why is that? Same thing. You are trying to remove a single negatively charged electron from an increasingly positive ion. So it's neutral for the first ionization energy, it's a +1 ion for the second, +2 for the third, so on and so forth. So that's why the ionization energies always get larger. But there is something else I want you to take a look at. You will note, for example, in magnesium that the taking away the second electron is pretty close to twice what the first ionization energy is. And that's what you expect from a doubling of the nuclear charge, going from 0 to 1. But there is a huge jump in going from the third one. Likewise, in aluminum, this is roughly tripling. This is you can see with the general increase, but all of a sudden, going from 1 to 2, that's a big jump. Going from 2 to 3, that's a big jump. Going from 3 to 4, that is a huge jump. And what you might notice is the huge jump in ionization energy happens one ionization later for each element. So what's going on here? So why is the third ionization energy for magnesium so much higher than that for aluminum? Valence electrons. Aluminum has 3 valence electrons. Magnesium has 2. So aluminum has a 3s2, 3p1 configuration. Magnesium is just 3s2. So when you move 3 electrons from aluminum, all 3 of those are still valence electrons. The third one in magnesium is a non-valence, or a core or inner shell electron. So what happens is that when you go from, after you've taken these 2 out, you're 1 level down, you're the next shell down. So you have lost a complete shell's worth of shielding. So there is a huge difference in the effective nuclear charge for magnesium and aluminum at that point. So this is a way of actually telling how many valence electrons an element has, is when you see the huge jump in the successive ionization energies. So with that information in mind, boron or beryllium, which is going to have the higher third ionization energy? So look at the periodic table. Boron is 3 elements in to the second row, implying that it has 3 valence electrons. Beryllium, only 2. Third ionization energy, so you're taking out 3 electrons. So for boron, all of those 3 are valence electrons. But for beryllium, that third one is a core electron. So the third ionization energy for boron is only 3660 kilojoules per mole. That's still a lot. But for beryllium, it is 14849. And that's the difference between taking out a valence electron and taking out a core electron. So be aware of that. And again, this lecture was started off with electron blue because we spent the whole day talking about electrons. All right, see you next time.